we might make a start, everyone. Thank you so much for coming. My name is Chris Gascoigne. I'm a Principal Solutions Engineer in our Cloud and AI Infrastructure Architecture team. You can probably guess from my accent, I'm not from the US, I'm from Melbourne in Australia, so it's really great to be here with you all today. This session, we're going to talk about AI infrastructure, and what I'm going to try and hopefully get across to you is not just what are the aspects of AI infrastructure, but more importantly, why does AI have different requirements on the infrastructure? What are the kinds of situations where we have those different requirements, and why do those requirements exist? So let's start off by talking about AI infrastructure. And the first thing I always say when I'm talking to organizations about the infrastructure to support their AI applications is that it really isn't a one-size-fits-all approach. And I think this is really important because a lot of people see these kinds of images from NVIDIA's GTC conference that they have every year, talking about these massive tens of thousands of GPU clusters, supercomputer clusters in giant data centers. And these are really important and really have a lot of use cases for specific organizations. But for most organizations, this is not what they want. For most organizations, that's really analogous to a Formula One car. And as anyone who's watched Drive to Survive probably knows, you don't just go out and buy a Formula One car. You actually have to build a Formula One team, which is very complex, very expensive, and requires lots and lots of people with very, very specialized skills. And so when we're talking about the infrastructure to support AI applications, what we should really be thinking about is what do we actually need for my organization and for my use case? And in some cases, it might be the Formula One car, but in many cases, it might be something much simpler and much easier to get started. It might be a, it might be a scooter, it might be a bike, it might be a regular car. Where on that spectrum do you actually fit? And to answer that question, you kind of need to know a little bit about how these AI applications actually work and how they drive the requirements into the infrastructure. And so I always like to go back to first principles when trying to answer these questions and actually understand, well, how do these AI applications actually work to have those different requirements on the infrastructure? So let's talk a bit about that, a bit about how these AI applications actually work. So I'll start off with this. So this is the first thing that any AI engineer or data scientist who's building out a new AI application and a new use case will start off with. They'll start off by deciding what is the architecture of the model that they're going to use in that application. And this is a very, very simple example. This is about as simple as it gets. This is known as a multi-layer perceptron. And this is a very small version of that. But this is still relevant. Even if you look at the large language models in use today, things like Llama from Meta and those kind of models, they still incorporate the multi-layer perceptron architecture inside those much larger models. So they're still very, very relevant today. And the basic premise behind these models is that we're going to, when we get to inferencing time, we're going to be passing our data through this model and getting some output at the end. But before we do that, we need to train this model. And the training process, basically what we're trying to do is, on this model, every single one of those linkages is essentially a weight. It's sort of how much influence does one neuron have on the input to the next neuron. And when we're doing the training process, essentially what we're trying to do is optimize those weights so that our model produces good output in a wide variety of scenarios. And so the way that we do, or the data scientists do that training process is through the training process. And basically during training, because you have a bunch of data, training data that has, you know what the inputs are, and you also know what the outputs are going to be, we can do things like this. So we start off by taking a sample from our training data set, apply that as the input to our model, run that through the model, and we get an output. If it's a classification problem, we'll get a label. If it's another type of problem, we might get a different output. But we get some output. And the first time we do this, because the weights on this model are not initialized, typically they're initialized to random values to start with, the output that we get the first time is going to be complete and utter garbage, completely incorrect. But because we're still in the training phase, we know what the correct answer should be. So we can actually look at what the model output, which is wrong, and what we expected the output to be, because we're working with our training data set at this point in time. And we can actually compare those two against each other. We can compare the expected output and what we actually got from the model. And then through what's known as backpropagation, we can calculate the error between those two things, between the expected output and the calculated output. And we can propagate that error backwards through the network. This is known as backpropagation. And essentially what backpropagation is doing is sort of taking that error and working backwards through the network and working out, well, which of those weights in the network had the most influence on the incorrectness of the output. And so then we can get a sense of, well, this weight had a very big impact, this weight had very little impact on the error that we got at the output of that model. And then using that, those sort of gradients, as they're called, we can do the optimization step. So the optimization step basically looks at all those gradients that we learned from the backpropagation phase and goes through and tries to update those weights just a little tiny bit every single time. Update those weights so that we'll get a better result the next time. And then we just keep doing that process. We keep doing that process over and over again, a few thousand times, a few 100,000 times, a few million times, a few billion times, depending on the size of the model, depending on the size of the training data set. We do that over and over and over, optimizing a little bit each and every time to make our model perform better and get more correct outputs. Now that all sounds relatively simple, probably not really simple, but relatively simple when we're talking about a fairly small model like this. But when we start talking about large models, very, very large models with very, very large training sets, we need to think about how can we take that training process that I just spoke about and distribute that across a cluster of nodes so that we can do our training jobs in a reasonable amount of time. Because there's no use having a training job that's going to take 3 years to complete. You need that training process to be much, much quicker. And so most of the time, what you end up having to do is do distributed model training. And when we're thinking about the distributed model training, essentially what we're trying to do, we're trying to start off with our training data and our untrained model that we talked about a moment ago. We're trying to produce a trained model, but we're trying to leverage multiple nodes to actually accomplish that. Now, those multiple nodes could be multiple servers, it could be multiple GPUs in a single server, doesn't really matter at this point. And essentially what we're trying to do is work out what's the best approach to actually do that. How do we distribute that training workload across multiple nodes so that we can improve the performance? There's a few different ways that can happen, that we can distribute the load across multiple nodes in a training sort of environment. There's a couple, there's one's called model parallelism, which kind of breaks the model up across the different nodes. But the most common and sort of building block for this is known as data parallelism. And the basic idea with data parallelism is that when I want to distribute that training process across my multiple nodes, I'm going to use the data, segment the data across all those nodes and run the training process in parallel. So in this example here, really simple example, we've got our training data, we've got 3 nodes in our cluster. Might be 3 nodes in a GPU, might be 3 servers, doesn't matter. We've got our 3 nodes, and what we're going to do is take that training data and break it up so that each of the nodes is working on a third of the data set. So the first node gets the first third, second node gets the second third, and the third node gets the third third. And then what's going to be happening is that each of those nodes is going to be doing that training process that we talked about on the whole model. So we're not breaking up the model in this case. Each node is working on the entire model itself, but using a subset of the data, and that's how we're going to do the distributed. But the question becomes, okay, if I'm doing this on my 3 nodes here, each of them working on a different section of the data, essentially a different data set, and they're training the whole model, how do I get that to produce a single model at the end? I don't want to get 3 different models. I want to get one model that incorporates the learnings from the entire data set. How does that actually happen? So I'll talk through how it happens in a GPU sense, and I'll go through this a couple of times to hopefully make it clear. So let's just go back a step and think about how we would do it on a single GPU in a single server first, and then we'll scale it up from there. So we've got a single GPU, we've got our model uninitialized at this point, and it's exactly like I spoke about at the start. That GPU will run the forward propagation phase where it runs the training data samples through the model forwards, calculates the error in the output of the model. They run the back propagation phase where they propagate the error backwards through the model and work out the gradients of all the weights in that model. And then the optimizer runs to update all of the weights in that model based on the gradients that we learned through back propagation. So that's how it works in a single GPU. Now let's come back to data parallel across multiple GPUs, in this case 3 again. Now the first example, I'm going to show you how it doesn't work. So this is the way that doesn't work, but the naive approach that you might think about. The naive approach you might think about is we have our 3 GPUs, we have each of those GPUs working on a third of the data because we've got 3 in this case, and we run the forward propagation on all those GPUs, we run the backwards propagation, and then we run the optimizer step on all of those GPUs. But because they're all working on different sections of the data, all of their new trained versions of the models are completely different. So we have that problem where we have 3 different versions of the models that we get. One that has the learnings of the purple data set, one that has the learnings of the orange data set, and one that has the learnings from the red data set. So how does it actually work? How do we do this in practice in a way that actually works, that produces a single model that has the learnings from the entire data set? Well, the way this works is the first 2 steps are the same. So with the forward propagation on each GPU using their own subset of the data, the backwards propagation, take the error, propagate it backwards through the network and calculate the gradients. But here's the difference. In data parallelism, what actually happens at this point in time before the optimizer starts is that there's a synchronization step that occurs across all those GPUs. And this is known as an all-reduce operation. And essentially what that means is that we want to reduce the 3 different sets of weights that we have across all those data sets. We want to reduce those to one set of gradients, and we want all of the GPUs to receive the same set of results. So we basically want to average, is the easiest way to think of it, average the gradients across all these 3 GPUs and distribute that average across all the GPUs so that they're the same. And the way that this is done in most environments, in an NVIDIA environment, is through the NCCL, the NVIDIA Collective Communications Library, implements this all-reduce operation across these GPUs. And it does it in this ring approach that I'm showing on the slide here. So instead of just sending all of the gradients to one GPU, having it do the average and then send them all back, because that would be very data intensive on the network, it actually uses this ring algorithm to do this synchronization step, where essentially what's happening is it will send a third of the data to the next one, and they'll send a third of the data to the next one, and they'll be averaging as they go. And it's a much more efficient way of doing that average operation. But now, essentially, at this point, what we have is that all of the GPUs have the gradients for all of those parameters in the model, but they're all the same because they're all an average of what each GPU has learned. And now, each of those GPUs then runs the optimizer step, just like we spoke about before. But because they now have the same average across all of them, when the optimizers run on each of those GPUs independently, they all produce the same result because they're all working from the same set of inputs. And so now we're all in sync. And we just keep doing that process again and again and again with more and more data to get the fully trained model. But the important point here, if I go back to this step, the important point here is that this synchronization step that happens between all of the GPUs is really, really important, because while this synchronization step is happening, all of those GPUs are essentially idle. They're not doing any calculations. They're essentially waiting for that synchronization step to occur before they can run that optimizer. And that's why GPU to GPU communication is really, really important in these training workloads. And it's also why we use this ring topology, which has an impact on how we build the networks as well. So if I jump forward, talked about that. Okay, so that's training. Inferencing is obviously much simpler. We all probably know that already, probably not news to anybody. But with inferencing, we already have our model architecture. We have trained weights for that model architecture that we've built up through our training process. And in the inferencing phase, obviously all we're doing is basically putting in our data on the left-hand side and getting a result, or a prediction, sorry, on the right-hand side based on the weights. So the input goes in, goes through the model, and comes out with the prediction. And that's all we need to do in inferencing. So obviously it's much less intensive process. I do want to touch briefly sort of a bit of a higher layer concept on this idea of retrieval augmented generation. If you haven't heard of retrieval augmented generation, you probably will fairly soon. This is an approach that enables, specific to large language model use cases, enables you to, I guess, augment a pre-trained model with your own data without going through a training process. So it's a really important point that I think a lot of people might be misconstruing. In a retrieval augmented generation system, a RAG system, there is no training that happens. It is all inferencing. We're essentially trading off, instead of doing lots of work at the training time and doing less work at the inferencing time, with RAG we're doing more work at the inferencing time to get an output that is more relevant to your organization as if it was trained on your own data. And the basic way that RAG works is that we have the large language model over here, just like we're probably all used to. But instead of just sending the user's request directly to the large language model, what we want to do is actually look up the information that's relevant to the user's question from some database and provide that to the model along with the question. So it can basically answer questions about information that wasn't in its training data set. And the basic way we do this is we use an embedding model to understand the context of the user's question. We use that embedding model to look up the relevant information from a vector database, and we then, based on what comes out of the vector database, we work out which are the most relevant results, and then those results are passed to the large language model along with the question so that it can generate the output. Now, the obvious question when we talk about RAG like this is, okay, that makes some sense, but how does the data get into this vector database? And to do that, we go through an ingestion process where we basically, take a bunch of documents that we're interested in, chunk those documents up into pieces that make sense together, whether it be paragraphs or sections or something like that based on the document structure. And then we use the embedding model to understand the context of each of those chunks and insert it into the vector database. So it's very much like an indexing process, not a training process. But there's a few things to note about this. The first is obviously, like I said, all of this is inferencing. All of these models are just doing inferencing. We're doing inferencing even at the indexing stage, that ingestion stage. We're using the embedding model and the vector database to actually do inferencing at that point to do those steps. And what you probably want to do is make sure that this, at the very minimum, the embedding model and the vector database, that should be close to where the data actually lives. That's really, really important because you probably don't want to be sending, gigabytes and petabytes of data, up to some cloud service using a REST API. It's not very efficient, very, very expensive, and you've got to keep doing that over and over again every time those documents change or every time there's a new document added to the repository. So that's retrieval augmented generation. All right, so let's come back and talk a little bit more about the actual infrastructure. I put this in here. Everybody obviously knows, when we're talking about AI and ML, we probably want to use GPUs to do both the training process and the inferencing process. I guess the point I wanted to make on this slide is that that's not a new idea. That's not something that NVIDIA just decided a couple of years ago when ChatGPT became popular. This is a slide from NVIDIA from 2007 talking about why GPUs are very useful in AI ML use cases. And it basically comes down to the fact that all of those, the inferencing operations and the training operations that I was talking about, they all basically can be decomposed into a series of matrix multiplication operations. And GPUs are very, very good at matrix multiplication operations because that's essentially what they were designed to do. So that's why GPUs are very, very good for doing AI use cases. And so when we talk about the infrastructure required to sort of support these applications, I put this together as a sort of completely genericized version of the kind of infrastructure that is typically used in these AI environments. There's a few things, I guess, to highlight here. So I've got a few servers. In those servers, at the top you can see they have CPUs like any regular server. Those CPUs have NICs attached to them, regular NICs, connected via PCIe to the CPUs, and those NICs connect to a front-end network, which is, we're all familiar with these kind of networks. It's where our management connectivity lives, it's where our connectivity to the outside world lives, it's where our storage in many cases might live, although not necessarily. Cluster management, Kubernetes, control plane nodes, all of those things will live on the front-end network. And then down the bottom here, this is where all the GPU stuff happens. So in this case here, I've got 3 servers, and I've sort of said each of those servers can have multiple GPUs, two GPUs, up to 8 GPUs, depending on the type of server. But there's a couple of differences. The first is that the GPUs inside the server have an intra-host interconnect, a sort of dedicated network to connect those GPUs together inside the server. In an NVIDIA scenario, that's something called NVLink. In a AMD scenario, that's something called Infinity Fabric. In an Intel scenario, they actually use Ethernet for that connectivity between the GPUs. And that's great for that all-reduce operation between GPUs that are in the same server. But if you're scaling that training job across multiple servers, then you need some way for the GPUs to talk to each other across servers. And NVLink doesn't really work in that way, and Infinity Fabric doesn't really work in that way. And so typically what you'll have is the GPUs will have dedicated NICs to connect to a special back-end network that is just used for connecting those GPUs to each other. And this is where the bandwidth and the speed of these networks really comes to the fore, because like I said before, when we're doing that all-reduce operation, the longer we wait for that to complete, the less efficient our GPUs are going to be, because they're waiting, they're not doing any calculations while that synchronization is actually happening. And so that's why these NICs are dedicated to the GPUs. They're typically directly connected, so you'll notice the GPU has a direct connection to those NICs. Their own dedicated PCIe connection. They don't go through the CPU or the host operating system. And they typically connect to these back-end networks at 400 gig and 800 gig fairly soon as well. So let's talk about when do you actually need that interconnect between the GPUs? When does it matter? Obviously it matters for training. I think we sort of talked about that quite a bit, and hopefully that's pretty clear. But when it comes to inferencing, do I need a back-end network? When do I need an NVLink between my GPUs from an inferencing scenario? And the reality is the answer to that question depends on the model that you're actually looking to inference. So if you're, I've got 3 examples here, and these are all based on Llama 3.1, just various different sizes of the model. So the left-hand side, we've got Llama 3.1, 8 billion parameter version of that model. And with floating point 16, FP16 precision, that model takes about 16 gig of GPU memory to inference. If any of you have sort of looked at this stuff in detail, you're probably saying, well, what about the KV cache? What about all these other things? I've got a big asterisk down here. We're ignoring all of that for simplicity. We're just going based on the model weights. So it's going to take about 16 gig. And if we've got a server that has 8 GPUs and each GPU has 80 gig of GPU memory, well, we can fit that model easily into a single GPU. In fact, we can fit multiple models into a single GPU at that size. And so in that case, GPU to GPU connectivity is completely irrelevant for inferencing. There is no need for one GPU to ever talk to another GPU. It's a purely horizontal scaling problem with nothing shared between any of those GPUs. If we go to a larger model, let's say we go up to the 70 billion parameter version of that model, again with FP16, that means we're going to need about 140 gig of GPU memory. That no longer fits on a single GPU. It has to be spread across multiple GPUs, but still fits within a single server. So in this example here, we can fit 4 versions of that model across those 8 GPUs in that server. But in this case, the connectivity between those GPUs inside the server does matter in that scenario, because there will have to be some passing of the parameters between the 2 GPUs. And then when we go really large, let's say we go to the 405 billion parameter version of that model, well now we can't even fit that in a single physical server. We actually have to extend that model across multiple servers, across 10 GPUs across 2 servers. And so in this case, the server-to-server GPU interconnect has an impact. And so that's kind of the point. Depending on the size of the model, in some cases, the intra-host and inter-host network is irrelevant. In some cases, the intra-host network matters, but the inter-host doesn't matter. And in very large scenarios, they both matter. And you have to think about both of those things. So when we're talking about those back-end networks and what can be used there, I want to talk about the requirements on that back-end network. What is different about that back-end network compared to the front-end network or traditional networks that we're probably all quite familiar with. And again, I like to go back to first principles and think about the why of some of these scenarios, because a lot of people say things about these back-end networks without ever actually understanding why those requirements exist. And a good example is everyone says, well, back-end networks need lots of bandwidth. Okay, that's true, but why? Well, I think we've explained why. That all-reduce operation that we talked about before that synchronizes across those GPUs between the hosts, the longer that takes, the longer the training jobs are going to take, and so bandwidth between those GPUs actually matters for that reason. And it's actually getting worse. I put this in here because I found this in a paper that as the model sizes get bigger, the amount of data transferred on the back-end network is going up 6 times faster than the size of the model. So if the model goes up by 1 megabyte or 1 gigabyte, the data transferred between the GPUs goes up by 6 gigabytes. And so the back-end network, the ability to transfer gigabytes of data from GPU to GPU becomes really, really critical. And from a network perspective, what does that mean we need on the network? Well, obviously we need lots of bandwidth, so we need 400, 800 gig switches and switch ports. But more importantly, we need to make sure that we can actually fully utilize all of that bandwidth in our fabric. So we need to have really good load balancing across our fabric. We don't want to have a situation where we might have 800 gig of bandwidth between two GPUs, but because all of the flows collide on a single link and we get congestion, we're actually getting less bandwidth available. So that's why things like dynamic load balancing, static pinning, advanced ECMP are really, really important. The second requirement that's always thrown out about GPU networks and back-end networks is they have to be lossless. Well, firstly, that's true, again, and the reason it's true is because the way that that NCCL operation happens to get the data from one GPU's memory to another GPU's memory, it goes over RDMA. And RDMA doesn't handle packet loss very well. That's ultimately what it is. And it doesn't handle packet loss very well because it doesn't have a very good retry mechanism. It has to wait for a timeout, and then it has to say, go back to the last packet that I saw and retransmit everything from that perspective. It has like a go back N mechanism. And so when there is packet loss present in the network, the performance goes down quite a lot. This is again from another paper I looked up. In an AI/ML training environment, even 2% packet loss can cause the training jobs to take 8 times longer, which is pretty significant. If you had a job that was supposed to take an hour and now it takes 8 hours, well, that's pretty annoying. If it was supposed to take a month and now it takes 8 months, that's not really sustainable, is it? So packet loss is important. That doesn't have to mean it has to be 100% loss. It just has to mean that packet loss is not routine in that environment. And the good thing is, from an Ethernet perspective, we know how to solve this problem. We solved this problem 15 years ago. Priority flow control, explicit congestion notification is the answer. You'll hear DCQCN talked about, and that's really just a description of how to use PFC and ECN together to achieve this outcome that RDMA over converged Ethernet actually needs. The third one is latency. Latency is important in AI/ML networks, but it's actually not as important as people talk about. It's important that the latency is consistent because we want to have good traffic flow across the network, but it actually, the ultra low latency is not critical in AI/ML networks because essentially what we're doing is bulk transfers between GPU memory of very large amounts of data, gigabytes of data. And the latency actually doesn't have much of an impact on the performance of that. So it's more about consistency of the latency rather than the absolute lowest level of latency. And I put in a fourth one here as a surprise because people don't think about this. But operations is really, really critical on these back-end networks. Because if you've got a back-end network that's supporting $10 million worth of GPUs, and that network is underperforming or deployed incorrectly or down, and your GPUs are not being utilized, you're literally setting money on fire because you have these very, very expensive resources that will be underutilized because the network is not performing. So automation, visibility, telemetry, all those things that we do in Nexus Dashboard are really, really critical to these environments. All right, so just a couple of quick key takeaways. like I said at the start, make sure you understand the workloads that you're going to be deploying and think about the infrastructure that will support those workloads correctly. It's not a one-size-fits-all approach. I find a lot of organizations that I talk to, they mention the word AI/ML and they get 50 server vendors descending on them saying, how many 8 GPU servers are you going to buy? And that is not the right approach. What you should be thinking about is, what is my use case? What does that mean from an infrastructure? Is it primarily inferencing? How large are the models? What's the usage going to be? And I can work out a much more optimal solution for those kind of customers. Don't get distracted by the latest shiny object. You see these NVIDIA GTC presentations, they look amazing, and they really are, but come back to reality, think what's actually required in your environment, what's going to align to your existing infrastructure strategy. And then finally, take advantage of some of the stuff that we've already done. We've got validated designs, we've got AI pods, Hyperfabric AI, these kind of solutions that make it easy to get from, I've got a use case, to here's the infrastructure that's needed to actually support that, and a validated design on how you deploy that to get the outcome without the risk. So, last thing, please complete your session evaluations, really, really important. I'm sure you've heard that a million times already. In terms of continuing education, obviously, we're sort of at the end, so make sure you check out the on-demand session. But I put in my email address down there. Feel free to email me, send me a message on WebEx Teams. More than happy to answer any questions that you might have from this session. Otherwise, I will say thank you very much for coming and enjoy the last little bit of Cisco Live before you go home. Thanks a lot.